Hello, my name is John Kemble, and along with my colleagues Justin Metzger and Rohan Walia, we are Chain Reaction. Our project was to create a Rube Goldberg device that would serve as a teaching aid for students. The objective was for a ping pong ball to enter the device on one side. Then the students would answer a series of questions where for each right answer, the ball would continue to progress through the system, where finally it would exit on the side opposite from where it originated. The different questions are to serve as a learning environment for the students, where they'd be able to learn while still being entertained. In our presentation, we'll be going over the final design for our project, as well as the educational aids that are provided with it, the concept generation, as well as the selection of, and the cost per unit, or to produce each unit, the product architecture, as well as a reflection of the final design and a reflection on the product design as a whole. Here's our project planning chart. Each blue square indicates something we've already completed, and as you can see, we're toward the very end of our design. We've already finished the product design and the presentation of the product itself, and we are currently in just the final presentation of our project. Just to recap, our customer is Mark Meyer, Superintendent for Montgomery County Public Schools. He has shown a very strong interest in providing equal resources to all grades to provide success. And we found that he would be a very excellent customer because if we were able to sell to him, we can sell to every school that he supervises. The other things that we've discovered during our product design is the customer needs, including interactiveness, safety, compactness, self-sufficiency, and cost effectiveness. We've also found that our target specification would include interactiveness, the audience age, and different STEM topics, just to name a few. Finally, our economic analysis included a break-even point of approximately 188 units. Here's a picture of our final design. The ball would enter here at the bottom of this semicircle. Then the student would answer a question on a computer where, based on a unit circle, how many radians this lever arm would have to turn to be able to push the ball onto this ledge and then let it go onto the next section. The second section was kind of based off a pool table, where the ball will go off this launcher against the edge of this wall and through this exit to be able to continue to section 3. For this problem, the students would have to solve the trigonometry equation, where we give them both sides of a triangle and then they'd solve for theta, theta being the angle at which this little launcher would be positioned. Our third section is is using a pulley but based off fractions, where we'd say there's approximately 60 grams that is able to lift 3 blocks. How much mass would be necessary to be able to lift a single block? Which, once they decide that's about 20 grams, they would place 20 grams into this low compartment. It would offset the pulley, thus knocking over this golf ball down the ramp, hitting the ping pong ball, and then exiting the device. Here's a picture of our final product where the first question would be posted onto the computer. The rest are labeled onto the device itself so nothing would get lost.
Here's our concept generation table. And so what this initially was designed for was to help us properly analyze whether our design concepts are targeting the specific components that we listed that are necessary for our target audience, which are 8th grade students who will actually be using the device. And so this allows us to tangibly see whether our device is hitting each one of those designated subfunctions and how they relate to each other. So each subfunction varies from the material to the topics covered to just how we actually construct the device itself. And so for station 1, you can see we focused on servos and the DC motor, since we knew that I wanted to use an Arduino. And then for station 2, it was a pool table-like design where a ball would hit an opposing wall. And so with that, the variations came into play with whether we wanted a barrier or not to make it more difficult for the student, or how the actual exit location of the ball would be located on the board. And then for station 3, that involved a pulley, and so the main consideration there was the material, because pulleys can be very difficult to make depending on the material that you use, and whether we wanted to show the algebraic equations of the problem, or if we wanted to emphasize the physics behind a pulley mechanism. Then each one of those designs would go into a concept selection table where we designate a reference design and then compare each of the other designs to that reference point. And from that, we're able to generate this ranking where we're able to cull the not so effective designs and then put those remaining concepts into a concept scoring table in which we weight each category and then come out with a number where we can see how they rank according to each other. And it helped us actually come up with the final design and choose what design we would go with for the final BRG. Here's our failure modes and effects analysis table, and this entailed analyzing the entire BRG as a whole and figuring out potential failing points. So our top three involved the Arduino and the servo motor found in station 1, and then the golf ball support found in station 3. So the Arduino was specifically risky just because it is a complex electrical component that the students can interact with and potentially misuse by unplugging different cords or accidentally resetting the Arduino or messing up the code. And the instructors might not be equipped to properly troubleshoot the device and maybe solve the problems that might occur. So then that might require chain reaction to send out a technician to actually service the Arduino. And then for the servo motor, the potential failures there are either the debris could get stuck in the housing, or the servo motor could misbehave because a student misused the device and potentially degraded some of the components inside, and then that would affect the questions that are then based off the Arduino. And these two functions are so important just because they're on the first initial station. So if one of these fails, then the student can't move on to the remaining part of the BRG. And then for the golf ball support, which is found right here, we found through our own testing that this joint actually weakened over time with the current support material we had. And so we had to increase the strength of that to improve the longevity of the support right there. And then when we calculated our final cost, it comprised of our assembly costs and the component costs. So the assembly cost was calculated by averaging the times it took for chain reaction to assemble the BRG ourselves. And we factored in an employee at this level who would be charged at about $15 an hour with a decent amount of work experience in this type of job. And so it's actually a relatively simple process just because the board comes pre-drilled with holes, and then each function has pegs that correlate to the specific holes in the board. However, the Arduino would take actually the most amount of handling time just because it actually has to be installed into the function or the station itself instead of going into the board directly. And then the launcher would take the most time to glue because once again, it has to be incorporated into the station itself and go into a proprietary hole where it would meet up in the groove. And then when we calculated the cost of our components, it was actually a relatively cost-effective design just because the majority of our material was cardboard. And so the most expensive component was actually the Arduino, and that's relatively understandable just because it is an electrical component that requires a lot of additional accessories. However, one way we could reduce this cost is by improving the manufacturing techniques of the cardboard and changing up the geometric layout for when we pre-cut it. And after you sum up the assembly costs and the component costs, we get a total cost of $35.45.
So for our final product, we decided to keep the product architecture fairly simple. It consists of 3 major physical chunks. Each represents a station, and each is also supposed to implement 2 functional elements. The first functional element is how the ball moves inside the station, and the second functional element is what the station is actually supposed to teach to the user. So for example, for the first station, the station allows the ball to enter into the entire machine, and the second functional element of the first station is to show the concept of angles to the end user. So our design is modular. and it allows for future improvements because each chunk is independent of the other, and designers can easily implement a variety of different concepts if they want to in future. Looking at our industrial design, the three most important aspects of our industrial design are weight, self-sufficiency, and ease of use. Our product is lightweight, made up mostly of cardboard. So that's what we planned. That was the goal for our project, and our product is also self-sufficient because all the accessories that are required to run the product are inside the kit. And our product is obviously easy to use because it's a fairly simple design, and we provide all of the instructions required to run the product. And we concentrated on safety. There are no sharp edges in any parts, and parts move at slow speed. The materials, again, we use cardboard, which is cost effective, readily available, and recyclable. Interactiveness, we have limited to 3 interactions so that users are engaged throughout the process, and also the number of interaction points make the design fairly simple. And in terms of performance, our product does not require a lot of power to run. The only part is Arduino that requires 5 volts to run, and so our product doesn't demand too much power. Reflecting on what we learned from this project, the first thing we would like to mention is that our product lacked some aspects of industrial design, primarily aesthetics, because we have a singular color tone, and we realized that we could have implemented a broader range of colors. And because our product is made out of cardboard, it's less durable than other products already out there in the market. We could have done a more rigorous competitive benchmarking and come up with and realize that we should have used a more broader color range. And same thing holds true for marketing plan. We would have come up with a better marketing plan that appeals more to the end user. And the constraints that we felt limited us in delivering a better product were the information regarding the development processes and the ability to work hands-on, and the time required the time given to us to actually come up with this product. We could have done a much better job if we had more time to implement those development processes, and we could have had a greater flexibility in prototyping if we had more funds. And we are proud of our achievements because we have met most of our important customer needs, including the weight, ease of use, and self-sufficiency. And the end product is actually, we set out with a manufacturing cost of $40, but we actually ended up with a manufacturing cost of $35.45. If you have any questions, we'd love to hear from you, and please forward your questions to us. Thank you.